Welcome to the Jack Westin MCAT Podcast with your hosts, Michael Maleka
and Molly Hudash. Well, hello, everyone. Welcome back to the Jack Westin MCAT Podcast with your hosts, Mike and Molly. Mike, this is going to be a really fun episode, right? We just talked all about redox, and now we're covering like the next logical extension of redox.
Right.
Tell us what we're talking about.
We are talking about something that I know you and I, like, we give like these free trial sessions on our Jack Westin page. If you haven't joined any of our free sessions, they're essentially like free lectures, like kind of a sneak peek of what, like how we teach in our actual lectures, because both of us teach. And so we've taught this probably over 100 times at this point, easily.
I know.
Easily. Like literally, this is exactly like over 100 times. And I think this was really cool because it's also a subject area. I feel like a lot of people, like, they think back to like when they took this in chemistry class, like way back, like it was like this idea that was really tough. And we're going to be talking about kind of like a double header today, where we're talking about redox potentials and thermodynamics and how they apply to batteries, like electrolytic, galvanic cells. And so this double header today is such a great build off of what we talked about with redox reactions last episode, which, if you haven't checked out last episode, what are you doing? Go back, watch redox reactions, where we talked about all about like reductions, oxidations, and we'll recap some of that today. But now we're going to be talking about why. Like, why is it that one material is reduced over another, and how we can apply those to one thermodynamics, all this idea about spontaneity and all those fantastic ideas, and then bringing them together, combining topic areas, and talking about batteries. Because I think this is a very MCAT relevant idea, where combining those content areas, any chance the MCAT can test you on multiple things at once, they will, right? Reason why the bicarbonate buffer system, they absolutely love it, because like we talked about before, which, again, if you haven't watched that episode, what are you doing? Go watch it. Combining all these areas together, I think batteries is another great place where you combine two really high yield areas of thermodynamics and redox reaction. So we've got a lot to be talking about today, and I think it's really, really fun to talk about these things.
Yes. Yeah. And so plus I feel like the word electrochemistry, which is what we mean when we talk about battery chemistry, right? That's how batteries power stuff. And if you have rechargeable batteries, that's how batteries themselves can be charged. I think electrochemistry, just as a word, is one of those things that kind of strikes fear for students. And it definitely was for me. We talk about this all the time, Mike. There are things that I hated when I was studying for the MCAT or when I was learning in undergrad, because I couldn't make it make sense. There was one or two things about it that just I couldn't wrap my mind around. And those are now the things that I absolutely love to teach, because now I get it. And this is one of those for me. Electrochemistry, I had a fundamental disagreement with.
Yeah, does not jive, not jiving.
But the way that you approach it is really going to shape how you understand it. So I'm very excited today. We're going to be walking through basically all of the required material that in itself is very high yield, that is really required to understand electrochemistry. So we're going to start off with really setting a very solid groundwork, building off our idea of what redox is, reduction and oxidation, right? Reduction, right? If you think of your Leo goes grr.
Oh, throwback.
I know, throwback. Leo, losing electrons means you're oxidized, right? Grr is gaining electrons, means you're reduced. Redox reactions involve the transfer of electrons. So in this first part, we're going to talk about how to tell which atom or molecule in a pair will be reduced and which one will be oxidized. We're then going to talk about spontaneity, right? And how spontaneity connects to this idea of redox. And then we'll talk about some cool biological applications, and we'll then get into electrochem. My favorite part is that we think electrochem is one of the scariest things we'll talk about, but really that's probably going to be one of the shorter segments of today.
Right.
It builds.
It builds. It's like, the kind of goes back to like the theme. If we have to talk about the theme of this podcast, it's all about intentionality.
Intention.
Right. Of course. You just knew what I was going with.
I knew where you were going with that.
And not memorizing. Like, we want to understand these things. And I think, again, electrochemistry is a great place where you can't memorize electrochem. Like, and again, we were talking about this before, I don't memorize anything when it comes to electrochem, because, and I mean, you're the same way, because if you understand the fundamentals, it just makes sense. It's like, there's no other way it could be. And so let's actually start with that foundation, start with this understanding, and let's start with like reduction potentials. So let's do a quick recap of where we were last episode when it comes to redox reactions. First, we'll talk about what a redox reaction is. It's the transferring of electrons, where one thing is gaining electrons, and therefore another atom must be losing electrons. When we talk about something gaining electrons, we say that molecule or atom was reduced. If something loses those electrons, we say it's oxidized, and that's why we have that fantastic mnemonic, which is Leo-Ger, right? Leo space Ger. Leo, losing electrons, is oxidation, space Ge, gaining electrons, is reduction. Again, we are Leo-Ger stands when in this at JW here between me and Molly. There's another one. Again, we don't have to talk about that other one. Actually, we probably
That
should.
oil
rig, whatever.
That
Because
oil
again,
rig thing.
that oil rig thing doesn't specify what you're gaining or losing, which is we beef with it. I mean, there's some oil rig people. You can let yourself know in the comments. But again, we're all about, again, this is this reaction where you're gaining electrons, losing electrons. Again, we could also view it as gaining hydrogens or losing hydrogens. And again, contrast that very clearly with acids and bases. Again, we went into this like last episode where we're contrasting with acids and bases, where acids and bases are always about gaining protons or losing protons, very different from gaining hydrogens and losing hydrogens. And you're like, oh, wait a minute, that's sounds kind of similar. Like, Mike, what are you talking about? Go watch the last episode. Go watch that last episode. We dove all about it. But this is kind of, again, a reminder that these redox reactions always also happen in pairs, right?
Yes.
You can never, ever have a reduction without an associated oxidation. Like you can't gain, like you can't just spawn electrons out of nowhere. If you're gaining electrons, you must have taken it from something else. Therefore, that lost the electrons. But then we have to ask the question, how do you know? Like, say you've got two atoms or molecules, you got two reactions, and you're like, okay, between these two atoms or molecules, which one gained the electrons? Like, which one wants the electrons more? We get this question, like, okay, how? So, Molly, say you're given two molecules, atoms, reactions, how do you know which one's going to gain the electrons?
I love this question because this to me was the fundamental thing that I didn't understand. That made me mess up in electrochemistry. And we'll hit on it again later, but the key thing, if you're deciding who's going to be reduced versus oxidized, is what the reduction potential is. And a reduction potential is a value. It's going to be a number, right? Positive or negative, and some value measured in volts. But before we get into numbers, I want you to think about the word reduction potential. It's a numerical value associated with your potential to be reduced. Leo-Ger says reduction is gaining electrons. So a reduction potential is how much do you want to be reduced, essentially, right? The thing that's very confusing to a lot of students is how to interpret these numerical values, right? So you may see a reduction potential of positive 2.54 volts. Okay.
Cool.
What does it mean to be positive? How is that different from negative 2.54 volts, right? Does positive means you're always reduced? Negative, does that mean you're always oxidized? No, right? The confusing part of this, and you can almost imagine it, put all these atoms and molecules on a number line according to their reduction potential. 0 on that number line is hydrogen. Okay, so what these are, all these numbers, positive, negative, that means nothing, right? It's all in comparison to hydrogen. So these values are relative to hydrogen. So positive 2.54 means that that atom or molecule wants to be reduced more than hydrogen does. That atom can be reduced or oxidized. Same thing with the one that's negative 2.54. That means that it wants to be reduced less than hydrogen does. It still means it could be reduced or oxidized. Okay. The positive and negative doesn't mean that you're always one thing or another. It's just relative to hydrogen. How much do you want to be reduced? So if we took that example where we have positive 2.54 and negative 2.54, right? And we wanted to figure out who's reduced and oxidized, you have to think who wants to be reduced more in that case. Positive 2.54
Or negative
2.54.
2.54. Well, because again, I always kind of like thinking about like which one has the higher potential to do the
Or
thing.
reduction.
Right?
Yeah.
Higher the potential to be reduced. That's the one. Like I always think about potential like, oh, if I have a high potential, whenever I go to a kitchen to eat a cupcake, when I go to the kitchen, what am I likely to do?
Eat
Go
a
eat a
cupcake.
cupcake, right? If I have a high potential to trip every time I leave my house, next time I leave my house, I have a high potential, I'm probably going to trip because I had a high potential to do so. If you're comparing two things and you're saying, okay, which one's going to be reduced? Look for the one that has the higher reduction potential or the more positive one. That's how I've always kind of like thinking about it.
If we're both in the kitchen and you have a high reduction or a high potential for eating a cupcake, but I'm also there and my potential for eating a cupcake is higher, I'm gonna go eat the cupcake. You'll be left without a cupcake.
Right, because you want it more. You
I want it
you got
more.
that dog and you just want it more. But so there when I'm comparing these two
God.
things, positive 2.54 and negative 2.54, well, the positive 2.54 wants it more. It has a higher potential relative to the negative 2.54. So that's why if it's reaction A, reaction A is the one that will get reduced, but then reaction B won't get reduced. Okay. If it's not getting reduced, then what must be happening to it?
So if you're not getting reduced, but you're participating in a redox reaction, then you must be losing that electron. Again,
Wait a minute.
it's
That's
always
called,
a transfer.
that means, wait, isn't that oxidation? Absolutely, it's oxidation, right? Like it's
Mhm.
like you have to have these reactions side by side. You can never ever have a reduction without an associated oxidation. And so if the positive 2.54, that's the one getting reduced, well then the reaction that's negative 2.54 reduction potential has to be the one that's getting oxidized, right?
Mhm.
But now this gets into another kind of idea of potential, right?
Mhm.
Because now, can you ever have two reductions side by side?
Mm-mm.
No, you can't. So it can't stay as a reduction.
Yeah.
We have to essentially change it to turn it into an oxidation. And we're kind of expressing these things as reactions, and these are normally kind of shown as two reduction half reactions. Again, if you're not sure about half reactions, go back to the last episode. But again, because they're kind of showing it. But if we want to change a reduction to an oxidation from a gaining of electrons to a losing electrons, what we have to do is we have to flip the reaction. We have to
And
flip.
to clarify, these half reactions we're talking about, you're going to see an atom plus an electron creates another atom, or a
Right.
molecule plus 2 electrons creates another atom. That's
Right.
what we're talking about with half reactions. You'll actually see an electron in there instead of 2 different atoms or molecules leading to 2 different products. So
Right.
one thing plus electrons gives you a product. That's the
Exactly.
half reaction.
Right. I guess I should have clarified, right? Because electrons are never part of the full reaction. Like if you see an electron in a reaction, you're not seeing a full reaction because we
The
don't normally
half,
take
yeah.
it's you're seeing a half reaction. And so if you see a half reaction and it's a reduction means the electrons are in the reactants, and you want to turn this into an oxidation, therefore the electrons must be in the products because you're losing them. In order to turn a reduction, half reaction, to an oxidation, half reaction, you simply just flip the reactants and products. I love that hand sign. Anyone watching just saw us both like in sync there. That's awesome. And so you have to flip the reaction. If it was atom 1 plus electrons leads to atom 2, well, therefore we have to flip the reaction. Therefore, it's atom 2 becomes atom 1 plus electrons. So we've just flipped the reactants and products. And we've turned it from a reduction to an oxidation. But if we flip the reaction, we also have to flip the what?
The reduction potential.
Exactly, because we're not seeing a reduction anymore. We're seeing an oxidation. So we need to turn the reduction potential into an oxidation potential. And how we turn a reduction potential to an oxidation potential is simply just flip the sign. So if it was before, it was negative 2.54, that was the one that was getting oxidized. Well, what's the oxidation potential now?
Then it's going to be positive 2.54.
Amazing.
Just the opposite.
It's just the opposite, right? And so this idea of the oxidation potential, sometimes I feel like that gets overlooked a lot because we're always like super focused on the reduction potential, the potential to get reduced. But we have to remember, like, if we're not seeing a reduction, it's not going to be a reduction potential. It has to be an oxidation potential, but it represents the same thing except to oxidation. It represents how badly does this reaction want to get oxidized. Right? And if something, and they're kind of like inverse of one another. If something's very likely to get reduced, it's very unlikely to get oxidized, and vice versa. If it's very unlikely to get reduced, like we just saw with this one, it was negative 2.54, doesn't really want to get reduced. Notice when we turn it into an oxidation potential, it's now positive 2.54. Oh, it really wants to get oxidized now. Makes sense.
I feel like it's useful to think about an example here, right? If we think of, and we're going to talk more about the electron transport chain. I don't want to get ahead of myself, but the end product of the electron transport chain is water, right? We're taking these electrons, they're flowing all the way through, right? We're harnessing energy, which we'll talk about, but the end product is going to be water. And that comes from oxygen accepting electrons and protons to form water, right? Oxygen, therefore, must have a very high potential for reduction. Very high.
Very high.
Right? And it's because oxygen is super electronegative, right? It wants to be reduced. It wants extra electrons. Think about trying to strip electrons away from oxygen.
Tough.
If it really wants to gain new oxygen or new electrons, excuse me, it's not going to want to give them up, right? You have to think of these things as inverse, right? They have a numerical value associated with how reactive they are with electrons, how much they want them, but also how much they don't want to lose them. I love that reduction potentials and oxidation potentials have the same magnitude, just different signs.
Just opposite signs. It's so great, especially when we get so convenient, especially when we get to the math about it.
Yeah, it could be like a negative log. It could be something ugly, but it's simply
the
same number, different sign.
Different sign, right?
Love
so
that.
Clean.
Love that for us.
And so love that. And again, loving these ideas because this kind of come back to what was the point, right? It is how do we decide if we have two atoms or molecules, what's going to be reduced, what's going to be oxidized? The answer is always what's the relative reduction potentials. The one that has the higher reduction potential, that's what will be reduced. The ones that has the lower reduction potential, it'll be oxidized. So let's do an example. You and me right now. Let's go through a scenario. I'll give you one and you give me one. All right. And we'll kind of go back and forth. So let me kind of think about it. So let's say I have reaction A. Reaction A, it's a half reaction, therefore it's gaining electrons, and it has a reduction potential of positive 0.31. That's its reduction potential. Now I have reaction B. It's a half reaction, also showing a reduction, right? But it has a reduction potential of negative 1.2.
Okay.
So both of them are showing reductions. But can they both be reductions?
No, they cannot.
So if one is positive 0.31 and the other is negative 1.2, which one, Molly, will be reduced?
So this is a good one to talk about because we have to ask ourselves, what is more important, the actual number or the sign, right? Positive or 0.31 is smaller than 1.2. However, we have 0.31 and a negative 1.2. Again, think about it on a number line. 0.31 is a bigger number, bigger, more positive number than negative 1.2. So 0.31, which is reaction A, that's going to be the one that's reduced, right? The one with the reduction potential of negative 1.2 is going to be oxidized. And it therefore, I know you're going to ask this next, would have an oxidation potential of positive 1.2. I knew you were going to ask that.
We have done so many questions. We have done so many, like, immediately, of course, that's what's the next question. What would be the oxidation potential? So perfect, right? And I love hitting on this example because a lot of people, we've seen this mistake so often where we see, oh, bigger number, therefore reduced. No, we have to pay attention to the signs. The one that's more positive will be the one that's getting reduced, right?
Yes.
So fantastic. Okay, you can hit me with one if you like.
Okay, let's try one where both are negative.
Okay.
Cool. So let's see what happens here. What if reaction A is 0.67 or negative 0.67?
Okay.
Reaction B, the half reaction is negative 1.4. What's going to happen?
Okay, so I have two reactions. Both of them are showing reductions, and one is negative 0.67 and one is negative 1.4. But I'm still coming back to the idea. I'm looking for the one that's more positive, and I'm thinking about it on a number line. So the one that's more on the positive side will be
closer to it.
Closer to the positive side, would be the one that's a smaller magnitude negative, right?
Mhm.
Because that's closer to the positives than my very negative thing. So
Mhm.
of the two reactions, reaction A, I believe with the negative 0.67, that is the one with the higher reduction potential, right? So that's the one that will be reduced. And it's my reaction B with the negative 1.4. That's what will be oxidized. So then, of course, the oxidation potential would be positive 1.4.
Yes.
Right.
Yes. And we will talk about how to put these things together in a moment, but I think it's really valuable to just really drive this home here. The positive and negative do not have automatic meanings. You can have two positive reduction potentials and still one will be reduced, one will be oxidized. You can have two negatives, one will be reduced, one will be oxidized. The positive and negative is simply relative to hydrogen. Okay, we're going to come back to this with electrochemistry. Again, that understanding that positive and negative are relative to something, right? We're talking about reduction potentials relative to a reference value. That is what completely broke my brain about electrochemistry.
Right.
That is the one thing that prevented me from understanding.
Mm-hmm.
So we will get there, but
Oh,
I
of
wanted
course.
to take the time to hammer that in again because that totally messed me up, right? So before we can get to electrochem, right, we've established what a reduction potential is. We've talked about calculating the reduction potential and the oxidation potential, and we are so close to being able to describe the energetics of redox reactions. But we should first talk about thermo, right?
Oh, I love thermo.
We talked about, okay, which one will be reduced and oxidized? Like, what will they do, right? And in effect, that question of who will be reduced and oxidized in order to carry out a reaction that wants to happen, that is thermo, right?
I mean,
Thermodynamics is all the whole essential question is, will this reaction happen? Yes or no? And essentially we're asking, who's got more energy, products or reactants?
I love talking about thermo because I love taking from like again, I'm a huge physics nerd. Huge. The way that you're a nerd about evolutionary biology. And again, I even regret saying that word because now I'm thinking, oh my goodness, we're going to talk about. I love physics. I love physics. And really kind of thinking about thermodynamics is realizing everything, everything is governed by these fundamental rules.
Yes.
Right? Everything's covered by things like delta G, delta H, delta S. The universe runs on this. And so when we kind of talk about these things, I want to recognize that everything follows these rules. This isn't just applicable to electrochemistry. This is applicable to every reaction, everything that happens. The reason your body works the way it does is by these rules. And if you really realize that you can apply these things to every single reaction, right? You like, especially, and we'll talk about, a great biological application really hits on these things. I think you like your understanding of physics as they apply to chemistry will just be that much more complete. A lot of these things can be a lot more straightforward. So I get just itchy just talking about this because I'm like, I love it so much.
I love it.
So let's kind of bring it back to kind of the point that you brought before about comparing the energy of the products versus the energy of the reactants. And I like bringing back to like our fundamental laws of thermodynamics, the fundamentals, right? And this kind of goes back to the law of conservation of energy, right? Because Molly, in the physics and thermodynamics that we know, right, can energy ever be created or destroyed?
Nuh-uh.
Absolutely not. This fundamental idea is foundational to energy because we are comparing, like you said before, right? Comparing the energy of the product to the energy of the reactants.
Yes.
But if there's ever a discrepancy between them, therefore, it can't have been that energy was destroyed or created. There has to be some explanation. And so let's say the products have more energy than my reactants, right? Well, could we have created energy as a result of this reaction?
No, but we could maybe have harnessed energy from something else.
Absolutely, right? That means we must have input energy in. Because again, we didn't create it. We must have added energy in order to make it so that these reactants that had a lower energy have a higher energy. Let's take the opposite. Let's say we have a reaction and the products have actually a lower amount of energy than my reactants. Well, did I just destroy the energy? Did it just disappear?
No, it must have gone somewhere.
It must have been released, right? This is the fundamental idea where energy is either as a result of a reaction, it's either one of these two things. Either energy was used, it was added or input, or energy was released. And this kind of goes back to like the foundational things where our universe always wants to get more stable. It always wants to get more stable. Stability means lower energy. The universe doesn't want a lot of energy. It always wants to get to a point where we have things that are less energy. So based on those two reactions, the one where we have a higher amount of energy in the products, or the one that we have lower amount of energy in the products, which one do you think the universe wants?
Oh, we want catastrophe over here. We want things to break down, energy to be released. That's the preferable stage.
Right. So we want it so that our products actually have a lower amount. We release the energy trapped inside. So now our products are very stable. So we always want a reaction where we had a higher amount of energy and we end with a lower amount of energy. And this is the idea, that difference in the energy of the products and reactants. That's the difference of our Gibbs free energy that we call it. And this is the idea. Maybe a lot of people have heard this, the delta G. Again, recognizing delta G is the difference between the energy of the products and the energy of the reactants, right? And this idea is really important because if you take that difference, right, of that lower energy minus a higher energy, what would be the outcome of that delta G?
If you have something small minus something big, you're going to get a negative value, a negative delta G, if you will.
Right. And that we just said that's what the universe wants. Therefore, negative delta G is what we call spontaneous. Spontaneous. We love that word, spontaneous. That means the universe wants this to happen. It will happen. We did not need to put energy into it. It just happens. Fantastic. Great. But therefore, we split on the other end, right? If we have a situation where our products have a higher energy than the reactants, well, the delta G then would be a big number minus a smaller number, 5 minus 2. Well, the outcome is going to be a positive sign. So therefore, this would be something the universe does not want. So positive delta G, we say, is non-spontaneous, right? And so it's this idea, this foundational idea of, because I'm sure so many people who are listening have heard these words spontaneous, non-spontaneous, maybe memorized negative delta G, spontaneous, positive delta G, non-spontaneous, but the why behind it, right? It's because the universe wants products that are lower in energy. Right?
Yes. And I feel like it's important here. We're not going to talk a ton about kinetics in this podcast, but anytime I talk about thermo, I always want to introduce a caveat. If you have a negative delta G, the universe wants it to happen, like you mentioned. We call it an exergonic reaction because energy is going to be released, right? Versus an endergonic, inside, energy is coming in, right? That would be something the universe doesn't really want to happen because it has to cough up energy to get that reaction to happen. Something that has a negative delta G is spontaneous. It will happen. However, it may not happen fast.
Yes.
Okay.
Yes.
There's two different worlds when it comes to chemical reactions like this. Thermodynamics is, will it happen? Yes or no? If it's spontaneous, yes. If it's non-spontaneous, no, with an asterisk.
Right.
We'll talk about coupling and enzymes in a future class, but the other realm is kinetics. The kinetic side of it is assuming the reaction will happen. How fast will it happen? So you can have a reaction that is spontaneous, even very spontaneous, like would release a lot of energy, but if it's it may be very slow. Okay.
Extremely slow. Right.
So just keep that in mind. Two totally different realms. You can have something very spontaneous that will never happen in your lifetime because the reaction happens
it's
so slow.
Right? Which this is a little bit counterintuitive to think that, like, if the universe wants it to happen, it should happen
Why doesn't
fast.
it happen fast, right?
It's this separation of the idea of
Two
thermodynamics and kinetics. And we'll talk about kinetics very future, very soon. And this actually also kind of reminds me about this kind of great point about like the delta G of the thermodynamics. It's thinking about it's funny, I actually just totally lost my train of thought there. That's actually never happened during the podcast before. I was like, I got distracted in kinetics. Now I'm sure it'll come back to me, but this actually leads us into, I think, some ideas that are also very important that are related to spontaneity, right? Which is the idea about, things like heat and how spread out the energy is. So let's kind of focus on this first part, which is the enthalpy of a reaction, or delta H. Now, how does delta G relate to delta H? Because I feel like a lot of these things are corroborated. They think they're like, I think they're mixed up a lot. And so I kind of want to realize they are related, but they are separate, right? And so when it comes to the enthalpy, right, how would you describe enthalpy, Molly?
So it's a change in the heat of a reaction, which I think is kind of abstract, right? I think it's almost worth introducing a little ahead of time the equation that relates these. You have delta G, which is the change in free energy. This is equal to delta H, which is heat energy. It's enthalpy, right? Which a lot of people think delta G and delta H are the same. They're not. That is one form of energy that we would take into account if a reaction has taken place. Typically, we're talking about heat released that is originating from bonds, right? And then you see plus T for temperature.
Wait. Minus.
Oh, minus. Excuse me.
Yeah.
Minus. Delta G is delta H minus T, which is temperature, times delta S, which we'll talk about in a sec. But I think looking at that equation from a bird's eye, you see delta G is a very general form of energy that can actually take multiple forms. Enthalpy, right, which is the change in heat, delta H, is one form of energy that can change in a reaction.
Right.
I feel like it's useful to introduce that just because it seems like, how are those two not the same? Especially because of the names endergonic, exergonic, endothermic, exothermic.
Right. It's the names I see switch all the time. So I kind of want to come back to that idea of delta H. The way I usually kind of think about them, I think about enthalpy as the energy in the bonds. Right? Energy in the bonds. That's what enthalpy really represents. Because you're right, the change represents heat, but enthalpy in itself isn't really heat. It's like the energy in the bonds, and we look at the difference of the energy in the bonds to know, was heat intaken or was heat released, right? Because again, we do that same comparison where let me look at the energy stored in my bonds and the reactants. Well, the energy in these bonds, and then okay, maybe I look at my products and now there's more energy in my bonds. Okay, wait a minute, like that's not, something's not vibing there because it's the exact same idea. Oh, well, therefore I can't have created energy. I must have added in energy in the form of heat, right? And then if I compare the bond energies in the other way, well, if there's less energy in my bonds than in my reactants, well, I must have released heat. And this is kind of where enthalpy and heat kind of correspond, where enthalpy in itself is bond energy, but whenever we look at the difference in, like, that's why we look at the delta H. Therefore, we look at, oh, was heat added or was heat released? And if heat was added, it's positive delta H. That means, the products had more energy than the reactants. Therefore, we call that an endothermic reaction. Again, therm represents heat. And so very different from endergonic, which is positive delta G. Endothermic is positive delta H. Other way around, if it's less enthalpy in the products than the reactants, well, the difference is negative. Therefore, heat must have been released. And that negative delta H is exothermic, right? As compared to exergonic in the negative delta G. And so again, I'm just really stressing, like, these are different things. And the question I always kind of like posing is, just because something is exothermic, does it necessarily mean it's exergonic?
No, because of that equation. The equation delta G is equal to delta H, right? So if that was it, they were equal. Yeah. Exothermic, exergonic, period. But it's not. It's delta H minus T delta S. So enthalpy change, right? If it's exothermic or endothermic, that is going to contribute to delta G, but we also have to worry about temperature and about delta S, which we haven't talked about yet, but it's about time.
It's about time we talked about entropy. Again, entropy is I think I love how the MCAT talks about it, because they just brush on the ideas of entropy. Entropy is something that's foundational to the universe. It's related to again, like I was saying, the same way you nerd about like evolutionary biology, I used to think I wanted to be like an astrophysicist as a kid. I nerd out about like the universe because it's this idea that the universe loves chaos. The universe loves chaos. It does not like having concentrated amounts of energy. No. it wants to spread out this energy. It always wants to, because again, I want you to imagine spread out energy is much more chaotic. I kind of compare it to my room, right? If I compare it to like my room, if I just let my room happen, there's gonna be shirts on the dresser, there's gonna be socks on the floor, everything's gonna be spread out. That's the natural order of my room. But I have to actually put in energy to actually organize my room, to make sure all my socks are in the drawer, all my shirts are hanged, my bed is made. In order to organize my room, that I need to actually put in effort. That's not the natural state of my, I'm gonna be completely honest.
Mike is messy.
I am,
Message
if I didn't put any energy, everything's going everywhere. Of course, I have to consciously put in energy, but I kind of relate that to the universe. The universe is messy. The universe wants to spread everything out. It doesn't like things in their own compartments. No, 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 that's too organized. No, no, let's spread it out, right? And this is the idea of entropy. We always want to make things more spread out rather than less.
Yeah.
And so if I'm thinking about entropy, I always want if I'm getting more spread out rather than less, and my products are more spread out compared to my reactants, and that's something I want. Something that's pretty favorable is an increase in the entropy or a positive delta S. This is very different than the delta G and delta H. Well, delta G, delta H, the things that want to happen are like negative. No, 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 not with entropy. In entropy, it's positive delta S. That's favorable because we want to get more spread out, more disorganized. Where a negative delta S means we're getting more organized or less spread out. That's not very favorable. And it's why, like in that equation, it's negative delta S contributes to favorability. And I think this idea of like the spreading out or the chaos to represent entropy is very, very important, not only for when we talk like right now for thermodynamics, but also when we talk about that biological application. Oh, don't get me started when I talk about entropy. But yeah, that's kind of like how I like to talk about it in maybe a little bit too much passion.
It's so funny because everyone that I have ever learned from talks about entropy as randomness and disorder. And I think if you pose that question to anyone listening, that's what they're going to say. I always think of entropy as freedom, right? Rather than like disorder, like, oh, I love chaos, throw everything everywhere. It's like, I prefer to be in a situation where I have a million different options available to myself. You know, think of like a kid. When you're a kid, I could be an astronaut. I could be an astrophysicist like you want to be. I could be an evolutionary biologist. I could be a veterinarian. I could be a doctor. I could be this. You have so much freedom, so many different ways that you could exist, right? You have so many different options available to you. That's very favorable, right? If you were like from the very beginning set in this little box of this is the only thing that you can do, that is a very, of course, a very ordered situation, but not favorable, right? If you think about a sodium ion in water, oh, it can bounce around, right? It can go anywhere that it wants, right? Because it can interact favorably anywhere, right? Versus something in like a sodium ion in a crystal lattice. Like it's pretty locked where it is, right? It's not going to move, right? It's very stable. It's right here. It's I'm staying, right? The more options, the more freedom that you have, naturally that will create more disorder and more randomness. But I feel like it helps me understand it more to rather than think like, oh, the universe just loves chaos. Throw socks on the floor.
Let's throw socks on the floor. I just really like
There's so
I
many
represent
other
the universe.
places a sock go than just my sock drawer. They could
of
go
course.
here.
My
They
socks
could go
are
in the
free.
sink.
They
could go on
free.
the roof.
I don't want now. See, people are gonna be like, "Yo, Mike just throws his socks in the sink
Socks on the roof.
Yeah, sorry, I'm just yeeting there over there. No, I don't put my socks in the sink, but yeah, I know what you mean. My socks are free, right? As they should be. As they should be. And this kind of brings us back to that equation of delta G equals delta H minus T delta S. We know delta G is the Gibbs free energy. We use this to know, does a reaction want to happen or not? This is like the ultimate decider.
Yes.
What contributes to that essentially decision, we have to take these two sort of halves into account. We have to take, let's take the bonds, like are we gaining or losing energy in the bonds? And then is the universe around it kind of gaining or losing energy? If that if between those two variables, it's favorable, well, then the reaction will be favorable. Well, if between those two variables, it's not favorable, like I could have something that's maybe the bond enthalpy, right? I have a negative delta H, which you would think sounds pretty favorable, but then my entropy, I'm actually getting more organized, and that offsets my my enthalpy. I could still be non-favorable even with an exothermic reaction. And so it's taking these two things into account that determine spontaneity. Minor note about the temperature, well, temperature's in Kelvin. Yeah, we have to always, and this kind of comes back to the ideas of chemistry and physics, units matter. Units always matter, especially when you're doing these calculations. Temperature here is in Kelvin, not Celsius. And that really matters here, especially when you do your calculations.
Yes. So super important to recognize that Kelvin, there's no negative values. The lowest that you can be is absolute zero, which we can't really even achieve right now at all. We can get close, but we can't. So temperature can never be negative, right? Which means that component of the equation, again, delta G equals delta H minus T delta S, that T can never be negative, right? So it's valuable to consider that, since the delta S, right, is ultimately deciding whether the sign of that portion of it. So something to keep in mind, right? That is Kelvin. It is never going to be negative, and it's probably not going to be zero. It's going to be some positive number. So the sign of delta S is going to determine what's going on with the with that component of delta G.
And that's a cool fact, like the third law of thermodynamics, that you can't actually get to zero. But if you were at zero, like you'd essentially have no entropy. But that's actually why you can't actually get, like, getting no entropy, no chaos is super hard.
We've gotten close though.
We've gotten close.
Cool. But you can't.
It's just like, it's like we with our human capabilities now, which would be, who knows in the future. So yeah, I think that's also cool.
I feel like it's really important that we've really made this point about delta G, because it's so fundamental. Like you said, you can apply this to really anything that happens in the world, in your body, in a metabolic reaction. You can get smaller and smaller in scope to individual atoms moving, or you can get larger and larger to, you know, mudslides and landslides. Like, it just is it favorable to happen? Yes or no? And as a result of that, because the scope can change so much, we don't only have one delta G equation. We actually have many. And you'll see this come up in a lot of different contexts, including one that's very related to electrochemistry and redox. But you might see delta G, and this is delta G standard, right? Is negative RT. R is the constant, T is temperature, ln, so natural log of KEQ. That's an equilibrium constant.
Yeah. For my lawn fans, I pronounce it lawn. I'm just going to say that.
Yeah. For all my lawnmowers out there.
For all my lawn fans, I say negative RT lawn K. I mean, if this, let me know in the comments if you represent lawn, or if that's just me.
Was that taught to you? Lawn?
Again, I've been doing this. I don't even know where I got that from. I've just always, like, it's like natural log has always just been lawn to my eyes.
Yeah, that's too, Yeah. How do you pronounce KEQ? Do you do Keku?
I don't do Kek, but it's like it's KEQ, but see, like, because with log,
not LN.
But see, with, like, imagine with, like, log, for example, you don't say LOG, you say log.
That's like a word.
Logarithm.
LN is not a
sure.
word.
Well, you know, it's the natural log, and I just like to pronounce it that way.
If it was LG, you would say LG, not LG.
What? I mean, maybe if it was representing log, I'd say log. Who knows? You know what? LN, you know, you can call it LN, you can call it natural log, or you know what? The MCAT doesn't mark you on pronunciation. You can call it lawn. I can promise you it'll be fine. But great way to remember, it's delta G naught equals negative RT ln K. Lawn K, long, I can't do it. It felt so long to say that. But it's lawn, not log, is the key.
Yes. Do we know that that's at standard conditions? Do we want to explain what standard is?
Okay, very briefly, because I see,
touch on it for us.
Just because I feel like it's like misunderstood. Delta G naught, it's not, when we mean standard conditions, delta G naught isn't actually at STP. That's not actually what delta G naught represents. All delta G naught represents is that the amount of products and reactants are equal. That's what delta G naught. So I kind of imagine like 1 mole of both. If you have the same amount of products and reactants, what's the delta G at that point, right? And so that's all I'll touch on right here. But again, I just want that to kind of sink in for a lot, because again, a lot of the times you just say, oh, delta G naught, that's the same thing as delta G. No. Because this relates to where your equilibrium is going to be, right? If everything is equal and it's a spontaneous reaction as a negative delta G naught, that means when you reach equilibrium and it went forward to the reaction, it went more to the products. That means when you reach equilibrium, you'll have more products than reactants. Therefore, it will be a very large equilibrium constant. And again, if you're like, how did you figure out that equilibrium constant? Products
Go
of
watch
reactants, but you
equilibrium.
go watch that equilibrium constant episode. We made one. It feels like forever ago now, but we made one. I promise to go back and watch that. But yes, it's related to when everything is equal, where does it go? If it was spontaneous, it was negative delta G naught, that means it went to the products. Therefore, if products are favored, very large KEQ, greater than 1. If everything was equal, delta G naught was positive though, it goes to the reactants. That means it's non-spontaneous, but rather that means it went to the reactants, it went backwards. Therefore, when you reach equilibrium, that means the reactants were favored, and therefore you'll have a KEQ that's less than 1, but greater than 0. This is how that delta G naught relates to RT log K. A big mistake I see is that people say it's delta G, and that is not correct. And so again, if I was like with students right now, I'm like, okay, let's do a problem to kind of show you what I mean. But yeah, that's just kind of a note with delta G. Since we're talking about thermodynamics, we have to mention it.
Yes. Yeah. And something to note is if you have a really big KEQ, because of the negative RT ln
Yes,
KEQ,
yes, let's go.
you would have a very big negative number, right? Which is why what you're saying is true, right? If you had a very big negative delta G naught, you'd have a large KEQ. That's the same situation. And this really governs, again, so many things.
Everything. Everything
Literally.
goes to equilibrium. Every reaction proceeds to equilibrium. So every reaction is governed by this rule.
Yes. Yeah, which is beautiful. And these are all reversible reactions. We could talk about things like ATP hydrolysis, which can go in both directions. We could talk about protein folding, metabolic reactions. It's always the case, right?
I guess I have a question for you about enzymes, for example. Do enzymes, because a lot of time we know enzymes are involved in reactions, of course, right? If let's say I see a reaction, right, and it's non-spontaneous, right? It's a non-spontaneous reaction, positive delta G. It doesn't want to happen. Can I make this reaction happen by adding an enzyme? Because we know enzymes, they catalyze a reaction. Can I make this reaction spontaneous now?
The answer is no, not really.
No.
The enzyme itself cannot make a non-spontaneous reaction happen. However, what an enzyme can do is take that non-spontaneous reaction, that positive delta G reaction that will not happen, and it can couple it to a spontaneous reaction. So can an enzyme make a non-spontaneous reaction happen? Yes, with an asterisk, only if it couples that reaction to another reaction that produces the same, if not more, energy that's required, right? An enzyme is kind of the middleman, right?
It kind of brings these things together, yeah.
Yeah, it facilitates a transfer of sorts. You need 10, whatever. You need $10. Cool. Well, I have this person that will give you 12. There you go. Right? Like its job is to facilitate. It can couple reactions, but if you had one reaction that required $10 and you had another one that only gave 8, nope, can't do
it's not going to happen. All right, and I think this comes back to this idea of delta G. Like we were talking about this before, where nothing that is net non-spontaneous will ever happen. That net word is very important. If you are net non-spontaneous, I don't care what happens, it's not happening, right? But it's this net idea that's very important, because we know technically non-spontaneous reactions happen all the time in the body. Things that don't want to happen. Take the human body, for example. Like, technically, I'm just a bunch of atoms. Like, but look how organized my atoms are, right? Like,
your atoms are so organized.
So organized. They are
like the most organized person.
What can I say?
Except your socks.
Except my socks. They're everywhere. But me, as a human being, my atoms are so organized. I mean, every human being is like that. But just about what we talked about, the universe doesn't like getting organized. It doesn't like, my atoms are trapped the way they are. But yet, I exist. So therefore, right, how did that happen? How did something that doesn't sound very favorable happen? It's because we coupled it. Because you hit on this term. Coupling means we took something that was non-spontaneous and we paired it with a reaction that was so spontaneous. It was more spontaneous than this reaction was non-spontaneous. So when you put them together, the net reaction was spontaneous. So therefore it happens. That's why we say that word net, because we have to, what's the outcome of putting these two reactions together?
Yeah.
But if I didn't have that other reaction essentially driving the non-spontaneous formation, I like this idea of driving it, well then it wouldn't have happened. And that's how non-spontaneous things end up happening. But if there's nothing to drive something that's non-spontaneous, it will never, ever, 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 ever happen. Ever.
Yeah. So if you have two different reactions with different delta G's, what you can do is add them together. If that added new value is less than 0, so it's negative, you have a net spontaneous reaction that will happen, right? If it's greater than 0, it's still non-spontaneous, right? It's still net non-spontaneous. It will not happen.
Never,
even though
ever.
you coupled it, it's not enough.
Exactly.
Right?
Exactly. Right.
Yeah. So we've talked about lots of different components with delta G, delta H, delta S, temperature, KEQ, all this stuff. I think we're finally ready to bring it back.
Oh, to redox. Absolutely. Absolutely. Because when it comes to redox reactions, well, these are reactions. And we just said that the rules of delta G, delta H, delta S apply ubiquitously everywhere to everything. Well, redox reactions are no exception. And so we talked about sometimes we have two reactions, two half reactions. One of them wants the electrons, one of them more than the other. Well, therefore, the thing that wants to happen is the one that wants it more will gain the electrons. The one that doesn't want it as much will lose the electrons. Therefore, that reaction must be what if it wants to happen?
Must be spontaneous.
It must be spontaneous. Now, just because we've introduced that word, now we introduce the ideas of delta G. But now we have just verbally connected redox reactions to thermodynamics. But we can't just do things verbally. There always has to be some link, equation-wise, especially when it comes to physics, that links these two. Molly, what's the link? What's the equation that really links these two ideas together?
So we talk about delta G as having lots of ways to solve for it, right? In this case, we have delta G is equal to N times F times E cell. So NFE cell, negative, right? N is going to be the number of electrons that are transferred in this redox reaction, right? So often it's 1, but sometimes you'll see 2 or 3, right? That will be N, right? F is Faraday's constant, and it's 96,500 coulombs per mole of electrons. I just say 10 to the 5th.
Yeah, like
Round
for
it up,
MCAT math, don't worry about that. Yeah, just it's 1 times 10 to the 5th.
10 to the 5th. And then E cell is essentially what is going on in that redox reaction. So E cell, and I know we both feel very strongly about this. There's a really common way to calculate it, which is actually fundamentally wrong.
It's so wrong.
It's wrong. It drives me nuts.
So wrong. Yeah.
The way that most people learn it is E cell is equal to E of or E at the cathode. Minus minus E at the anode.
Yeah, so you notice like we like struggle with it because we're like we never use this reaction.
Cathode and anode we haven't talked about yet. We'll mention it. Reduction is going to happen at the cathode. It's red cat. Oxidation is going to happen at the anode. The problem fundamentally with that way of solving it is we are assuming that both things are being reduced. You're using the reduction potential for both. So you have E of reduction at the cathode, which happens, red cat, yes,
right,
minus E of reduction at the anode. But the anode, it's red cat and ox. The anode will always have oxidation, period.
Always.
That's
Always.
it.
So are we using reduction potential?
You'll never have reduction. So why are we using that?
So
how do we do it then?
So the other way that we do it is it eliminates these kind of like, I don't know why we use that method. Because again, another skate at that method is because the negative is there. Because notice you had to be so careful with what you said first.
Yes.
Right? I don't even realize, again, we've been teaching so long, how many people make the mistake of switching them around because the order matters.
Minus E cathode.
Again, the order matters for that equation. It's again why I don't want to use that, because there's so many places you can make an error. But rather, we use the fundamentally what's the true reaction, what's happening, where the E cell, the total potential of this reaction is the E reduction plus the E of oxidation. How badly does this want to be reduced? Plus how badly does this want to be oxidized? You put them together, now you have the E cell. And what's great is because it does fundamentally what a redox reaction is, where it pairs a reduction with an oxidation. That's fundamentally what you have. And then what's great is this is an addition reaction. So it doesn't matter which order you put first. You can put E-ox plus E reduction. It's an addition. It doesn't matter the order. So you will get the right answer right away. And what's great is because we already talked about finding the oxidation potential, where whatever is the lower reduction potential, you flip to make it the oxidation potential, and you simply add them together, right? And so
let's just give them a quick example,
Sure,
right? If
sure.
we had two reactions, two half reactions, we'll go nice round even numbers.
Yeah.
One had a reduction potential of positive 2.5, and the other one had a reduction potential of negative 2.5.
Right.
What would the E cell be?
Well, all right, I'm thinking, okay, first I need to decide which one's reduced, which one's oxidized. We talked about which one has the higher reduction potential, the more positive reduction potential. That'd be my positive 2.5. Well, therefore, my reaction that's associated with negative 2.5, I need to turn that into an oxidation. Well, therefore, I need to turn this reduction potential into an oxidation potential. So I take that reduction potential of negative 2.5 and I have to flip it. I have to flip it in order to make it the oxidation potential. So now it's positive 2.5. Well, now to find the E cell, I add the reduction potential and the oxidation potential. So it's positive 2.5 plus positive 2.5. Again, it's no longer negative. I already flipped this to the oxidation potential. So my total E cell would be 5 volts or millivolts or whatever my units were. And so it's this idea where you're doing what's truly happening, not a shortcut with cathode and anode. It doesn't matter the order, but by doing it this way, again, the amount of errors I see with this way is so much fewer. So people might ask, do I need the other reaction, the E cath minus En? I have never, ever, ever seen a scenario where I needed to use that I couldn't use E reduction plus E oxidation. I don't know about you, Molly, but I've never used them.
Nope.
Yeah. So I always kind of suggest to my students to forget about the E cathode minus E. I just forget it, throw it out. You don't need it. Throw it. Just because another mistake I see is that people try to keep both in mind and they mix them up.
Worse.
They mix them up, and that's just worse. Choose one. If you're like Mike, Molly, I really love my E cat minus En equation. You know, all the power. Or I learned it and I'm just so used to it. Amazing. All the power to you. Forget about the E reduction plus E oxidation reduction, because again, when you try, I see so many people do both, like flip the oxidation yet still do the minus, right? Choose one and then stick with it, and then forget about the other one.
Yes. Right. Yeah. We have our preferences, but
of course, like yogurt, oil, oregano as well.
Exactly. Yeah. So that's our main link, right? We can now, with an idea of the reduction potentials, we can tell you not just which reaction or who will be reduced and oxidized, but we can also now quantify based on those reduction potentials how spontaneous this reaction is going to be. So very, very cool. Lots of opportunities to do calculations here. And the math is not super awful. So I feel like you see this calculation not incredibly often, but you know, it's pretty fair game. It's pretty for a calculation question.
You can see it quite a bit. And actually, before we move on, we should actually also note something when it comes to the electrons.
Yeah.
Right?
Oh, yeah.
That's a really important point. So this is something that's very important because we talked about combining a reduction and oxidation reaction, right? If a reduction is happening, you combine it with the oxidation. Great, to get the full reaction. But before you combine these two half reactions, you have to make sure that the electrons match, because the electrons, the reduction is gaining has to match the electrons that are being lost. So say I have two reactions where one reaction is gaining 2 electrons and one reaction is losing just 1. Well, right now I have a mismatch of what's being gained and lost, and therefore I have to make it match before I combine my reactions. So in this situation, reaction A is my reduction and is gaining 2 electrons. Reaction B is my oxidation. It was only losing 1. Therefore, with reaction B, I have to multiply it by 2. I have to multiply the whole reaction by 2 in order to make the electron match, 2 and 2. But then a mistake I see way too often is, well, if I multiply my reaction, do I also multiply my reduction potential? Right? Yeah. And the answer is no. Do not multiply your reduction potential or your oxidation. You do not touch that thing.
Yeah.
Right?
Except to flip the sign.
Except to flip the sign. Sure. But the magnitude, because I always kind of think of it as like a likelihood. I always think about it as a likelihood. Because like say I flip a coin. What's the chance it lands on heads?
50%.
If I flip 3 coins, each one has what chance to land on heads?
50%.
Let's do 1,000 coins. What's the chance that each like one lands on heads?
Well, now it's 0.2. It's just
No.
It's 50%.
50%. Just because I've done the reaction more often doesn't change the likelihood or how much it wants to land on heads or tails. Doesn't change the amount the reaction wants to be reduced or oxidized. So just because I'm multiplying by 2, 3, 4, you do not touch that reduction potential. Again, I see this mistake because this process looks a lot like calculating enthalpy, right? When you're doing those reactions for calculating the total enthalpy, and like that's what's the law? It starts with an H.
Wait, what?
Oh, for calculating the enthalpy law, like, if you find all the individual reactions, you find the total enthalpy of the reaction. Is that Hobbes' law or Hess's law? Hess's law.
Hess's law.
Right, that's the one I'm looking for. So yeah. So Hess's law is if you add up all the enthalpies of the component reactions, you get the total. Kind of related today, but that's like a whole other conversation. For those reactions, if you multiply it, you would multiply the enthalpy, right? Because more reactions are happening, more heat will be produced. But that's where I see people like overlap the two. No, with enthalpy, you do one thing, but with reduction potentials, you do not touch those. You multiply a reaction, you don't touch your reduction or oxidation potential.
Except to flip the sign.
Except to flip the sign.
We always have to highlight that.
We always have to
That's
flip.
fair
Yeah.
game. You can do that. You can do that.
Please, yes. Yeah.
Okay.
Go.
We've got so much momentum, and I know I really want to get to electrochemistry, but I have to. I'll be quick. I have to talk about the electron transport chain. And
I'm so happy. Let's talk about it. Yeah.
I love this. This really gets me going, right? I love, especially
this and evolutionary biology.
reduction potentials in the electron transport chain. I love it. Really, aerobic respiration as a whole, right? Going from glucose and oxygen to water and carbon dioxide, right? Which is why we breathe in oxygen. It's why we breathe out carbon dioxide, right? It's why we eat things like, potatoes and apples that have glucose in it, right? Stored in starch. That is one giant redox reaction. We break it into a billion smaller steps, and not all of those individual steps are redox. But if you consider glucose and oxygen to carbon dioxide and water, that's redox, right?
And you could prove that actually using the that we talked about last episode. Oxidation numbers. You could use the oxidation number. Yeah, I'm like trying to do a callback to last episode, but I'm like, you probably have no idea what I'm trying to say. Yeah, you can prove that using oxidation numbers, because we talked about last episode, like how to know if a redox reaction occurs. Well, don't take our word for it. Look at the oxidation numbers of the oxygen before in the glucose and the oxygen after in O2 or in H2O, and you can kind of see how it's changed, right? So yeah, don't take our word for it. Prove it yourself.
I thought you were going with the idea that glucose to carbon dioxide, we talk about how losing electrons means you're oxidized, but then also the trend is losing hydrogens means you're oxidized, or gaining bonds to oxygen. So glucose, C6H12O6 to CO2, you're losing all your hydrogens, gaining new bonds to oxygen, so you're being oxidized.
Sure.
O2 to H2O, you're gaining bonds to hydrogen, you are being reduced. That's where I thought you were going, and I was like, that does not connect.
I was going with the oxidation numbers, but see, there's so many ways that you can show that this is just a big redox reaction, which I think is super cool. And again, there's so many steps. And again, also I really like thinking about the fundamentals, like where is the energy stored in a glucose? Because we talk about the energy stored. It's in the electrons, in those bonds with the electrons. So of course you want to take those electrons. Wait a minute, taking electrons. Wait a minute, that sounds like a redox reaction. So again, really speaking to what we are going to dive so much more into the aerobic respiration in some later episodes that we have planned out. So we don't want to dive too much, but yeah, no, super important since we're on that topic about these reactions.
Yeah. And because it's a little bit more individualized, although we will talk about it a lot more, when you think of the electron transport chain, the whole reason why you can pump protons in the electron transport chain, which will downstream make ATP. Keep in mind, ATP synthesis, very non-spontaneous. That does not want to happen, right? Taking 2 negatively charged phosphates attached to ADP and shoving a third one, no. We do not want that, right? Requires a lot of energy input. The energy comes from the electrons. And I think the coolest connection, because we know intuitively that the electron transport chain it harnesses the energy from those electrons that will ultimately be used for ATP synthesis. The actual reason why the electron transport chain again, and I don't want to say creates or produce as energy, because it doesn't. But the reason why it's able to harness that energy from the electrons is because we start off with electrons bound to molecules that have very low reduction potentials.
They don't need them that much.
They have electrons, but they don't really want them. And the electron transport chain is the most beautifully complex little game of hot potato.
Oh, the hot potato example.
I want this electron. Here, you take it. I have a low reduction potential. Let me pass it to something that has a higher reduction potential. That is energetically favorable, right? That energy is used to pump protons. That next one is like, I have an electron. I don't really want it either. Here, you take it. Pass it to something with a higher reduction potential. That releases energy. The energy is used to pump protons. It's this huge, I mean, you could think of it hot potato. You could think of it like a ball rolling down the stairs, right? Every time an electron is passed from something that has a low reduction potential to something that has a higher reduction potential, energy is released. And those electrons are all going to end up bound to oxygen to make water. And we know oxygen is desperate for the electrons.
Right.
Going from things like NADH and FADH2, which can accept electrons, but don't really want them. And therefore, that's very high energy, right?
Yeah.
All the way to oxygen, which wants them so bad and will take those electrons even if there's very little energy left. That process is so spontaneous. That energy is used to pump protons, and then those protons are used through ATP synthase to make a non-spontaneous reaction happen.
Yeah, so cool. It's the couple so well, right? It's so,
I couldn't not talk about it. I
know
love the electron transport
I'm
chain.
so happy you did, because again, it really links as well redox reactions to spontaneity, right?
Yes.
Because, right, like these reactions, we know you and I exist, we happen, we have energy, therefore we know this is spontaneous, we know that this is going down. But why is the electron transport chain important? I always kind of love asking this question to students, like, what is the purpose of the electron transport chain? Well, it's not, again, stay with me for what I'm about to say. The goal of the electron transport chain is not to create energy, is not to create ATP. That is not the goal, right? That's the job of ATP synthase. ATP synthase is not part of the electron transport chain. I will die on this hill. People are like, oh, it's part of the, no, but it's not. Because again,
it's not.
Yeah, it's
uncouplers will prove it. No, they're
it is
tethered,
definitely not.
But they're not the same.
It relies on it, right? Because we have to remember what the ETC stands for, the electron transport chain. It's part of it's anything that receives an electron in this chain is part of the chain. ATP synthase never gets an electron, so it's not part of the chain. So then if it's not to produce ATP, that's the job of ATP synthase. What's the goal of the electron transport chain, right?
It's to take that energy stored in electrons and pump protons.
Pump protons, right? It pumps protons up a gradient. And I always kind of like starting here, because I'm thinking, wait a minute, up a gradient, that means I'm taking protons that were kind of with, and I'm pushing them, storing them, and organizing them in this compartment in the mitochondria. And does that sound very favorable to organize them?
Yeah, and because they're all positively charged ions that want to repel each other, that sounds quite unfavorable.
Unfavorable, right? It goes against the laws of entropy. We're organizing things, right? It sounds nonsense. This shouldn't be possible. Well, therefore, we have to couple it to something that is spontaneous, right? Which is these redox reactions that we just talked about, that they're always going from lower reduction potential to higher reduction potential, which we just talked about is spontaneous. We just talked about is favorable. So this is the electron transport chain is just a giant coupling situation, or that we've talked about before, coupling this non-spontaneous thing of bringing protons up their gradient with this very favorable redox reaction, right? And it's just this chain over and over, something favorable coupling with something non-favorable, and then by the end, those really high reduction potential oxygens take those electrons and carry them away. And so it's this idea that it's just a giant coupling thing, that there's that's why, again, I'm in love with energetics, because again, it just applies to everything. And I think it makes it make a lot more sense why these things happen. Again, going back to this idea that don't memorize the electron transport chain in that way, right? Know the why, the purpose, the why is it happening the way that it is. So no, you love the electron transport chain. So do I. It's such a great application. Such a great application. Yeah.
It really is. And we will talk about it in more detail in the context of metabolism later. Right. And we will even talk about coupling in more detail along with kinetics.
Oh, yes.
In a future episode.
Maybe sooner rather than later. Who knows?
Maybe like next week.
Who knows? Right? Wow.
But I think at this point, we've laid such important groundwork. We've talked about reduction potentials. We talked about how to figure out who will be reduced and oxidized. We talked about how to calculate each cell, how that relates to thermodynamics, all the applications of thermodynamics. We talked about biological applications. We're ready to finally tackle what I always saw as like the biggest beast of general chemistry, which is electrochemistry. Again, to reiterate, this topic scared the you-know-what out of me.
Right.
Because
the tardigrade out of you. Who knows?
It broke my brain because there are things about these electrochemical cells that are always true, and they were in conflict with how I understood reduction. Okay, so we've set all the groundwork. Let's start off with just the basics, right? So what is electrochemistry? What does this mean? What are the types? What should we know about this at the beginning?
Right. And so I kind of like think about electrochemistry first in like where you see it in the world. And I think of it as batteries. I mean, maybe this will be the thumbnail related to your picture of batteries. I don't know. But when we think about electrochemistry, a great way to think about them is batteries. Because the goal with electrochemistry is to turn chemical energy into the flow of electrons. That's the goal, right? We want a flow of electrons as a result of these different potentials. And when we talk about batteries, we have two types of batteries. We have galvanic cells, or also known as voltaic cells, and we have electrolytic cells. So it's important that we start about like, what are the two types of cells? And let's start about like kind of what the main point about them is that one is spontaneous. The galvanic cell is the spontaneous cell. That means the reaction that is occurring is the one that wants to be occurring, right? And so when I take my phone right now, anyone who's like who's listening on video right now, let me actually have my do not disturb on, right? If I turn on my phone right now, my phone is on. I have electricity flowing through the LED bulbs in my phone screen, and they are going where they want to be going. They're happening spontaneously. But if my phone dies, I need those electrons to go backwards. I need them to not be where they are right now and go back to where they came from, where they didn't want to be before. And so I had to plug it in, right? And so this is the idea. And then I'd turn my galvanic cell into an electrolytic cell, because now I'm forcing the thing that doesn't want to be happening to occur. And this is why we say galvanic cells are spontaneous, while electrolytic cells are non-spontaneous. The thing that does not want to be happening is occurring, but then we have to figure out how is that happening. Okay, well, so that's kind of like the first place to start, knowing the two types of cells.
Yes.
Yeah.
And I feel like it's important. We talk about it as spontaneous and non-spontaneous, but I love that you bring up your phone because the same components can be used to make a galvanic cell or an electrolytic cell, right? The same atoms. Again, if you had two atoms or molecules, one had a higher reduction potential, one had a lower, and therefore we should convert that to an oxidation potential, right? We know spontaneously this thing, right? Reaction A wants to be reduced. Reaction B wants to go backwards and be oxidation. That would be set up in a galvanic or voltaic. That's the other name. They're the same thing. That's a galvanic voltaic cell. If the thing that is being oxidized or reduced wants to be reduced, and the thing that wants to be oxidized is being oxidized, that's spontaneous.
It wants to be happening. Yeah.
If I somehow plug in an external power source, I can force the opposite to happen. Same component atoms or molecules, but I can now force the thing that wants to be reduced to be oxidized.
Right.
And I could force the thing that wants to be oxidized to be reduced. That is non-spontaneous. But if you plug it in, or if you create an external source of energy, it can be used to couple it and force the reaction backwards.
Right. There goes this idea of coupling once again, causing something that's non-spontaneous, something that does not want to be happening, to happen by coupling with something that is very high in energy, like plugging it into your wall. And so I love that. Yeah, we're talking about these. It goes back to these reduction potentials. What wants to be happening versus what doesn't want to be. So electrolytic, high reduction potential isn't getting reduced; it's getting oxidized. Versus galvanic, right? The high reduction potential is the one that's getting reduced. It's so critical.
Yes. And this is what broke my brain. Okay. So I want to go through what is always true and then what is different between electrolytic and galvanic, because this caused me so much stress. Okay. What is always true. And this doesn't matter if we're talking galvanic voltaic or if we're talking electrolytic. The anox red cat works. Okay.
Always.
Anox, again, ox starts with a vowel. It has to be an. Anox. You can't have a ox. You can't have red ox, right? Anox. Or you can't have an cat, I guess is the idea.
Yeah, that would be the idea.
Anox, anode houses oxidation. Red cat, reduction happens at the cathode. Anox, red cat, always true. It doesn't matter. Okay. Reduction happens at the cathode. Oxidation happens at the anode, period. Okay. What you will also see is that electrons are going to flow from the anode to the cathode. Okay. And again, it makes sense because oxidation, you're losing electrons. So electrons are
leaving, right?
Where you have oxidation and going to where you have reduced or reduction.
Where they're gaining the electron. So it goes from where they're leaving to where they're gaining. Of course, that always has to be true.
Yes. And as a result, right, because we're losing electrons and therefore whatever, ion or whatever atom has lost electrons is now becoming more positive. What we see is in a galvanic voltaic cell, we have something called a salt bridge that is going to allow anions to flow to the anode. Because again, anode houses oxidation. We're losing electrons. We're becoming more positive. Those negatively charged anions are moving to the anode to balance that out. Same deal. We have cations that are accepting these electrons to form a new, let's say, metal. Cations from the anode are moving to the cathode. Okay. So the other thing that's always true is anions are attracted to the anode. Cations are attracted to the cathode. Those are things that are always true.
Right.
What broke my brain was that in a galvanic cell, we see the cathode being positive, the anode is negative.
Oh, and positive, negative what?
That's what broke my brain. So I thought cathode was positively charged. Anode is negatively charged. But if the cathode is positively charged, why the heck is it going to attract a cation, which is also positively charged?
Yeah.
It made no sense. Made no sense. How could it be positively charged and attract something that's positively charged? That fundamentally and in terms of physics doesn't make sense. The thing that you need to remember is these positives and negatives are not charge. Positives and negatives reflect relative reduction potentials. What that means, if we're saying that the cathode is positive in a galvanic cell, which again is spontaneous, if you compare the reduction potentials of the two things that can be reduced or oxidized, right, your two reactants, if you're positive, it means you have the larger reduction potential. Positive means you want to be reduced. So cathode being positive makes sense.
Makes sense. It's totally just what we talked about at the beginning of today's podcast.
Yeah, that would be spontaneous. The thing that wants to be reduced and therefore is positive is being reduced. In an electrolytic cell, which is again non-spontaneous, you require the input of energy. What you're going to see is the cathode, which keep in mind that will always house reduction, period. The cathode is negative, which means the thing that does not want to be reduced as much, again, positive and negative are arbitrary. They're just positive is the thing that wants it more. Negative is the thing that wants it less. The thing that does not want to be reduced as much is being reduced. The positive thing that wants to be reduced is at the anode.
Being oxidized.
Yeah, it's being oxidized. That is why. Positive and negative do not mean charge. That's going to break your brain. Positive and negative are relative to each other. Positive is who wants to be reduced. Negative is who wants to be reduced less or would be happy to be oxidized.
And I think this is where, like, again, where I hate memorization, because that makes so much sense. Because if you try to memorize this, you're going to mix it up. I can promise you, you're going to mix it up. You're going to think, oh, electrolytic, oh, is it positive, cathode, negative? Because you're not really understanding the why behind it. If you understand, oh, galvanic, the thing that wants to be reduced is getting reduced. Oh, the one with the more positive reduction potential. Oh, of course the cathode is going to be positive. Oh, the electrolytic, the thing that doesn't want to be happening is happening. Oh, the thing with the more negative reduction potential, oh, that'll be reduced, right? If you come at it with that understanding, like that stress associated with the exam, in that high stress scenario, you don't have to rely on your memory. And again, it really is important that you commit to this idea, because if you do, again, that's we've just finished
That's it.
electrochemistry.
That's
That's
literally the
it.
whole thing.
That was, again, electrochemistry is this huge thing. We just, I think, how was that? Like not even 10 minutes, like that to talk about that. But
But
it
that's the
really,
beauty of it.
it's the beauty of it because it relies on those fundamental understanding pieces, right?
Yeah.
Where again, it's all about reduction potentials, and it's those reduction potentials that allow electron flow, right?
Yeah. And
Um,
spontaneity.
and spontaneity, right? The thing that wants to be happening or doesn't want to be happening. And I
Yeah.
think you put it really, really well, Molly. The thing with the salt bridge, I think it's important to know why the salt bridge is there. Like, why is it important that the anions go to, the anode, the cations go to the cathode? Well, it's because in these cells, we actually want to maintain neutral charge. We actually don't want charge differences, because imagine if at the anode we're losing electrons, I'm losing a lot of negative charge. Well, therefore, what will build at the anode is positive charge.
Mhm.
That would be a problem, because then I'm not creating a battery anymore. I'm creating a capacitor, right? Because now I'm going to have a separation of charge. So I actually want neutral charge. But therefore, I need to put negative back. I'm losing electrons. Then you got to put negative back in. That's the point of the salt bridge. Why anions go towards the anode is to give back that negative charge to keep it neutral. Same way with the cathode, right? Electrons are going towards it. So you'll get a lot of negative charge if you don't do anything. But this is why you have the salt bridge. So those like cations can go there to balance out all this negative that it's gaining. So the idea of the salt bridge is to keep the charge neutral, right? That's the why behind it. But also really, I actually have never heard like that anion to anode, cathode to cathode. But that's great. That's a great way to think about it. I've never heard of that. Yeah.
Yeah. I mean, so you just summed up beautifully why we build. We
Right.
build, we discussed electrochemistry that itself could be a billion, a very, very long textbook chapter. I personally was very scared of electrochemistry. I tried to learn it as a standalone topic without first looking at
Yeah.
redox reactions and truly understanding reduction potentials. And that's why I could never make sense of it, because I didn't understand what was going on at a fundamental level. I jumped straight to the last chapter of the Gen Chem book and tried to
Oh
learn
my
it on its
goodness.
own.
Yeah, no.
And you can't do that. These ideas build. And the beauty is we could cover, redox is pretty early in like a Gen Chem textbook, which by the way, we just posted a whole bunch of free textbooks
Oh
if
my
you guys want
good.
them.
Absolutely. Absolutely.
Unintentional, but amazing. And they're free. So go check them out. Right. Redox is pretty early in a Gen Chem textbook for the MCAT. Electrochem is at the very end. If you skip to the last chapter, you're going to miss out. Right?
Of course. Right.
I've tried to make sense of it. I've tried to shove it in my brain. It doesn't work. It doesn't work. And that memory is not stable enough to last you until your test day. Right. It's very easy to mess with, and it's very easy to decay because you don't have true understanding to strengthen it. Right. You're not going to retain something you never understood to begin with. So thank you guys for listening as we go through many high yield topics to build to this very high yield topic here at the end. I love that we covered basically 3 lectures in one.
It's like all at once, but they just tie in so
But
well.
they tie, yeah,
So
it's so
well.
beautiful. And so we've done in this process a very thorough cover of redox and electrochemistry, which are pretty tied. We also covered all of thermodynamics. Our next episode is going to get into the other world.
Oh, the other world, the one that we kind of referenced a little
upside
bit.
down.
Right. Oh wow,
No.
what a call! What a call! Wow, what a reference.
Thermodynamics again is all about, will a reaction happen? Yes or no. It's all about energy, right? Is it spontaneous? Is it not? The other world is kinetics.
Right. The speed.
Assuming it happens, how fast can I make it happen?
Right. We're going to be talking about it's so important, especially it builds so well off thermodynamics. So we'll be talking about kinetics, but then we have to be talking about enzymes next episode, because those are so related. And I think there's a lot of misconceptions about enzymes and things we like always take for granted when it comes to enzymes, and enzymes are a huge high yield topic on this exam. So I'm super excited to be talking about it with you next episode.
I know. Get excited, you guys. And if you missed our episodes on redox or on equilibrium or whatever, or if you want to go all the way trawling in our past episode history, we've also covered so many amazing things like how to study content, how to review practice exams, how to use Anki for retention.
That's a popular one. A lot of people really like that one.
Yeah, we covered a lot of strategy at the beginning here before we embarked on our content journey. So if you're joining us for the first time, highly recommend. I think we started in like February.
Oh, that's a
something.
Throwback. I can take a look. I want to say
Our
January or
first couple
February.
episodes together, I
Yeah.
think the first like maybe 10 or so are all strategy. We really
Mhm.
cover every level of MCAT studying. So
Mhm.
if you are just getting started on your journey, go check those out as well. Tune in for the content ones, but also
Yeah,
check
of
out the
course.
strategy ones. We talked about how to learn, how to review passages, how to take
Mhm.
passages, all of those good things. So
Mhm.
thank you guys so much for joining. We hope you join us for the next one.
Mhm.
And until then, Mike, what do we say?
Happy studying, everyone. Again, is that happy
We'll
studying,
find
everyone.
out. We'll find
Wherever
out.
we catch you, I hope you're having a great time studying, whether it's the morning, afternoon, evening, middle of the night, which I hope it isn't, because get some sleep.
Go to sleep.
But yeah,
Yeah.
we'll catch you in the next one, everyone. See ya.
Bye.